Alright, so let's go through the Charles of 2 2020 H2 physics question. So the very first part, they ask us to state how a stationary wave is formed. Okay, so for these 2 marks, when two identical waves traveling in opposite direction with the same speed, frequency, amplitude, and wavelength superposed. So this will actually cause a stationary wave to be formed. Okay, so for part B, a vibrating tuning fork is held above the top of a tube immersed in water. So definitely, right, the tube and the tuning fork are gradually raised together until a loud sound is heard. When you hear a loud sound means resonance occur, and of course, a stationary wave is formed. So the loud sound indicates that a stationary wave is formed in the tube, and this longitudinal stationary wave is represented in this figure 4.2. So you can see that at the surface of the water is node, at the top, at the opening of the tube, right, is empty node. Yeah, so of course, why is it being represented as a transverse wave? Even though we know that sound wave is a longitudinal, because it's for easy visualization. Okay, then for the very first part, we are asked to describe the representation in figure 4.2, which illustrate a longitudinal wave. Okay, for these 2 marks, so you just need to say the particle at the node is not oscillating. Okay, then we must also mention the antinode. While the particle at the antinode is oscillating at the maximum displacement about equilibrium in the vertical direction, because it's a longitudinal wave. So means for example, right, we have a sound wave traveling in the vertical direction. So we must mention the particle oscillate in the same direction or in the parallel direction. So yeah, this is imperative. Okay, so for part C, complete 4.3 to represent the lowest frequency of a stationary sound wave in a tube that is open at both ends. This one also simple. So just remember all the boundary conditions. So so the lowest frequency, right, means that the first stationary wave is formed. So for example, I just draw the node here. I draw antinode here. So this will be the first stationary wave. Okay, then for this is a dotted line. Okay, so that is for part C. Okay, for part D, the frequency of the stationary sound wave that is drawn in part C is known to be 540 Hz. So the frequency of the sound in the tube is now gradually increased until the next stationary wave at the next highest frequency is formed. So determine the frequency. Okay, so to do this question, we can simply just first we let the tube, right, to have a length of, let's just say, L. So this is L. Okay, so just by looking at this stationary wave, you can see one thing, right, is that this is 1/4 of a wavelength. This is another 1/4 of wavelength. Means that the wavelength you see, right, inside this open tube is half a wavelength. So half a wavelength, right, represent your L. So means that your wavelength in terms of L, right, is 2L. So this is the wavelength of the first stationary wave. Okay, why do I need to do this? Because very simple. I need to determine the speed. The speed of the sound wave will always be the same. So regardless of the frequency and regardless of the wavelength. So for example, right, V equal to F lambda, where F is 540 Hz, the wavelength is about 2L. So I just represent the speed of the sound in terms of L. So 540 times 2, about 1080L. So that is the speed of the sound wave, which is constant because you are always in the air, right? Okay, the next thing, I want to determine what is the next frequency where the next stationary sound wave will be formed, right? Okay, first I simply just draw a simple sketch of the stationary wave. So for example, right, okay, so this is the first stationary wave. Of course, I must respect my boundary condition. So for example, right, okay, so this part, I have 2 nodes here, antinode here. The opening must always be antinode. So I simply draw like that. So this is my second stationary sound wave. So I draw this one. Okay, so this will be the second stationary sound wave. Okay, so by looking at this, right, we know that this is L because it's the same tube, right? Okay, then we need to determine how many wavelength do you see in this picture. So you can see, this is half a wavelength, then this is 1/4, right? So in total, is actually 1 wavelength. It's a full wavelength. So means that this thing is wavelength L. Okay, so now I want to determine the frequency. So speed equal to F lambda. So my speed is the same, 1080L. 1080 L. So my wavelength is in terms of L. So of course, frequency is simple. It's just frequency equal to 1080 hertz. So that is how we actually do this question.